Hello everyone, so today we're going to be looking at how liquid water evaporates from a pool in a tube with stagnant vapor phase, while a stream of dry nitrogen flows to remove all the moisture at the top. And we're going to explain what the driving force is for this evaporation and the diffusion of hydrogen and nitrogen. Then we're going to write down the pertinent equations and explain the gradient of nitrogen concentration limits itself toward diffusion towards the pool, but results in a net nitrogen flux of 0. So, first let's draw out our situation as we're going to have like this barrel kind of thing with water at the bottom. Then we'll have a screen here. It's very important to remember, with nitrogen flowing over top, that dry nitrogen, and then a mixture of hydrogen and nitrogen in this area right here. So first we're going to go over Fick's law, which is very important to this equation. So Fick's law thoroughly explains about how things diffuse a bicomponent mixture diffuses in an open atmosphere. So this J is the molar concentration times the diffusion coefficient times the first molar component with respect to dz. And again, Fick's law is just the natural occurrence of a high concentration area flowing towards a low concentration area, which is very important in this sense. So you may be asking yourself, how do we get that negative C value? So negative C is the molar concentration. So we have this N value over, so we have moles over a volume. So if we think back to our ideal gas laws, think of Pivner. PV equals nRT. So mole over volume is actually just N over V. So let's separate this out. So we have this RT divided by RT, and then we have divided by V. The P over RT equals N over V. So this N over V is kind of hard to figure out, like how many moles are in a certain area and everything. However, P over RT is something that we can measure very easily too, as we have the pressure, temperature, and then the ideal gas constant, or the gas constant, not ideal. So that lets us be able to figure out the concentration much easier. So now the total concentration, we'll represent that by C total. If we think back, is actually our C value of nitrogen, concentration of nitrogen, plus our concentration of water. 20. And now we can replace that C value with PRT. So if C total is equal to the pressure of nitrogen over the R value temperature of nitrogen plus the pressure of water times the R value times the temperature of water. But then it's also important to note that because we have that screen that we mentioned here earlier, we actually don't have to worry about a pressure gradient. So we'll put that as this delta P does not, DNE does not exist. That's very important to note. So there will be no pressure, nitrogen or pressure, water. It'll just be, so we're really only concerned about that temperature. So with this in mind, we don't really, the only gradient we're looking at is the concentration gradient in steady state. So with that in mind, let's look at a graph to kind of figure out better about how these look. Better water versus our nitrogen. So water is pretty self-explanatory as it goes from one point and then it diffuses down. However, nitrogen acts a little bit differently in this case, as nitrogen diffuses like so, almost in a curve like, but then it still increases overall. With this in mind, nitrogen kind of acts as a sort of differing factor as opposed to the water or the diffusion. So think of like an elliptical. So the water or the diffusion rate is moving in one direction, but the nitrogen is moving in another direction, but it's fundamentally not moving. It's staying in place. Just like as you would be moving on an elliptical, the water is moving, or the diffusion, is moving, but not the nitrogen. That's very important to note here. So with this in mind, how do we prove that the nitrogen is a net zero? How do we prove that it's actually staying in place? So let's derive this out. So first we have this N value, put a little line here, is equal to N1, or water, plus our N2, which is our nitrogen. So our nitrogen is equal to 0 here. This N is still non-zero. It's a non-zero value, so we not exactly sure what it is, but we know that this nitrogen is 0. It's a net 0. Which takes us to our next equation, which is this N2 is equal to our molar flux, JN2, plus our YN2, which is our molar diffusion of nitrogen, times our N2 plus NH2O, or water. So we know these equal 0. So we have 0 equals JN2, YN2 times NH2O. Subtract that to the other side. So we have negative NH2O, or negative YN2 times NH2O is equal to JN2. Fundamentally proving that while nitrogen is continuously replacing the diffused water, it is 0. So it's just replacing, it's not moving forward towards anything, which fundamentally proves that there's no net nitrogen flux here. So again, to reiterate, it is like an elliptical where the nitrogen is moving in one direction, but it's staying still, moving against the current or the elliptical, or however you want to think about it. So it's a very important factor to keep in mind here as we go forward. Hello everyone, so today we're going to be going over what we just derived but we're going to have our diffusion coefficient at 10 to the negative 5 meters squared per second. And we're going to estimate the molar flux of water in a tube with a vapor length of 1 meter at 50 degrees Celsius and 1 bar. So to kind of get a picture of what our problem is, I'm first going to draw kind of a situation that we're working with. So our tube, we have more like a box almost, because that's what we're just working with. We have water down here. We have a mix of water and nitrogen. And then we have that nitrogen is flowing over. Let's mess up. So actually this length right here is 1 meter, or our vapor length. So this is the situation that we're in. We have our water, our mixture, our nitrogen flowing over, our dry nitrogen, and then our vapor length of 1 meter. And again, to kind of write it out and get organized, our diffusion coefficient D is equal to 10 to the negative 5 meters squared per second. Again, diffusion's area over time. Our vapor length, 1 meter. Our temperature is 50 degrees Celsius, or 273 plus 50, which is 323 degrees Kelvin. And then our pressure is 1 bar. So our driving force in this is our concentration gradient. So it's important to note this, as it'll be key in our equation going forward. And I'm going to denote this with the gradient symbol with that upside down triangle. So again, what is concentration, right? Concentration is moles over volume, which if we go back to our ideal gas law, PV equals nRT, we can divide that RT over, and then divide that B, where we get P equals RT is equal to N over B, or moles over volume. So concentration for measurable is pressure over a gas constant times temperature. And lo and behold, we have our pressure and our temperature, and then obviously we always have our gas constant of 8.314. So, however, partial pressure is still needed here. And partial pressure, we can use this by using our Antoine and Cauchy-Clapeyron, or even shortcut equation if we really wanted to. So Antoine, as we know, we can kind of get these values from a variety of different places. Online works, but it's a log 10 base with our P saturated is equal to our A value, which these are all specific to whatever you're working with, minus our B value, and then T, which is sometimes in Kelvin, sometimes in Celsius, plus C. Our Cauchy-Clapeyron relates two different temperature and pressures. So we have natural log of P2 over P1. That's equal to the change in enthalpy in the vapor phase over R. And then that's times 1 over T, T1 minus T2. Typically that 1 value is our reference point. So our reference point in the clash clock run will be that one value. That would be, our temperature that we already have. And then to get that second pressure, we could use that temperature that we already have and vice versa. Right? So to kind of go through the math, kind of skip ahead a little bit, I'm going to have it solved it. So our pressure for the water is 12 times 10 to the third pascals. And this is again at 323 Kelvin. So thinking back, we can now calculate our pressure of the nitrogen, as we already have our total pressure. We have our pressure of the water plus our pressure of the nitrogen. So our pressure total is at 1 bar, which is, in other words, 1 times 10 to the fifth pascals. And now we have 12 times 10 to the third pascals of water, and then plus pressure of nitrogen, which gives us our pressure of nitrogen is equal to 88 times 10 to the third pascals. So, using that information, we can solve for our molar value of nitrogen. So I'm going to clear up a little bit of space right now. So now we're going to use our original equation that we're going to do to solve for that molar volume, for that molar value of water. So this NH2O is equal to our negative total coefficient times the diffusivity, the diffusion coefficient, times the of dy of the H2O, again it's gas, over with respect to position, and plus that y value of H2O times our molar fluxes of NH2O and the nitrogen. So again, that nitrogen is 0. Our concentration, if we remember, is that P over RT. So we could simplify this, or expand it, I should say, into negative P over RT. We have our diffusion coefficient, our derivative with respect to position, and then plus that y value, H2O, times our molar flux of water. So now we can subtract this over, where it gets us N H2O minus Y H2O and H2O. That's equal to our negative PRT times our diffusion coefficient times our derivative with respect to position. That's it now. So, we can simplify this out a little bit. We can take that out, NH2O, and then that's times 1 minus Y H2O is equal to PRT D YH2O dZ. And then we could divide this over, and then we're going to bring that dZ over. So to make our derivative a little easier. So NH2O dZ negative PRT and we have DYH2O over that 1 minus YH2O. So now we can integrate both sides. And for reference, that PRT, that's constant. Our temperature diffusion coefficient, that's constant. So really, we have, this is our derivative. So now we can integrate that out to get the following. So I almost forgot, we got to get rid of that dy H2O to derive this. So what is the dy H2O, or the YH2O? YH2O, uppercase Y, is equal to pH2O over the total pressure. So we have 12 times 10 to the third over 1 times 10 to the fifth. So that gets us 0.12 total. So now we have more balance to what we can figure out what would be our derivative here. So in essence, this is actually more like 1. Making sure I don't make that same mistake. So this helps us at z equals 0, y is equal to 0.12, and z equals 1, y is equal to 0. So now that we have bounds on our equation, we can figure out this derivative right now. So we have our N H2O. We're bounded from 1 to 0 dz. We just used it here. And that's equal to negative Vd RT. And we have 0.12, 1 over 1 minus y H2O. TyH2O. So, I'm going to clear this up and we can break down this derivative. So, now we have this NH2O. When we derive that out, it just ends up being 1. And then we have our more complicated side, this negative PD RT. And then we get ln 1 minus YH2O. That's evaluated at 0.12, 0. But we have a negative that cancels out, so we get the following. YH2O, this one, 0.120 power. So, next step will be to evaluate this at its correct form. Which we can use our natural log rules to get the following. So as a reminder, this is NH2O equal to this negative pressure. Excuse me, not another negative there. To where we get 1 times 10 to the fifth. Our diffusion coefficient. Which is 10 to the negative 5. And then that R value is 8.314. Then our temperature is 323 Kelvin times ln 1 over 0.88, which is equal to 4.76 times 10 to the negative 5. So you may be asking yourself, how did we get here still? What are our units? That's a very important question. So first, for that pressure value, we have 1 bar, which can be equivalent to pascals. Of force over an area, which is kilograms times meters square seconds, which is our force, which is essentially weight times acceleration. So our next portion, and then that's over an area. So then it's our 10 to the negative 5th, which is in meters squared per second. And then we have our gas constant, which is joules per moles Kelvin. And what's joules? Joules is newtons per meter. Which is equal to kilograms times meter cubed per second. So we have on the bottom this kilograms times meter cubed per second, and then we have Kelvin. So let's get this all together, which will get us kilogram times meter squared times second squared times mole times Kelvin. Now on the bottom, we have meter times second squared times kilogram squared times meters cubed times Kelvin. So now canceling these out, we can get rid of our kilograms, we can get rid of our kelvins, we can get rid of 2 of our meters, and then we can get rid of these seconds as well, leaving us with just moles meters squared per second. So our final answer is 4.76 times 10 to the 5th moles meters squared per second. So that is our final answer of the flux of water with a vapor length of 1 meter at 50 Celsius, 1 bar, and a diffusion coefficient of 10 to the negative 5 meters squared per second. Thank you very much.